Okay, so demotion is the next one. Moving common functionality lower in the physical hierarchy. So what does that look like? Suppose I have an event queue and an event. And the event queue knows about events in the interface, but the event knows about the event queue because the event queue has some common stuff that's shared by all the events. So what can we do about that? Well, we clearly have a physical cycle. We don't want that. And here's the example listing. And here's the common event info. And here's the way we access the common data. This is how we have set up our components and classes. And you know, whenever you start designing with the idea that both things know about each other, you're going to wind up with physical cycles. So we have to do something about this. This is the runtime look. This is not a component diagram. So you have to be able to switch between the runtime diagram and the static diagram. This is a runtime diagram where we have an event queue object pointing to a bunch of events via some sort of list object. Okay? And each of the event objects points back to the event queue. And everybody knows about everything, right? We don't want to do this. So the trick here, I say trick, the technique is to create a new entity called common event info, which is much like taking the guts out of a container and putting it below the container, where event would have the role of iterator and event queue would have the role of the container. So this is just like that. And now what's happening is we have this kind of dependency. The event doesn't depend on the event queue at all. It depends on the event info. All right, so what does that look like? Here's our levelization. And we're going to go back and look at the new diagram. And it now looks like this, or not diagram, but the new components. We have 3 components. And we're going to instead look at the runtime. This is the old one. We're going to do the magic and now see we're actually pointing at an object that's contained by the event queue. We're pointing at the event queue info object. Does this make sense? This is classic, by the way. When you have something that points at something else that points back at the first thing, but not all of it, this is how you fix it. So it looks like this. Now, does this make sense? This is a very common pattern. It's when something points to something else and the other thing points back to part of the first thing. Take the first thing out, make it a lower level component, and then embed it in the object, and now you've got a clean dependency graph. Okay, that's all. That's all there is for that. Any questions? Okay. All right. Remember I talked about uses in the interface in name only. Opaque pointers takes advantage of that. So I was asked a question at the break about what happens when you have an account and a person, and they both need to know about each other. So let's take the example of a manager and an employee where they both need to know about each other. And the example here is that a manager manages a bunch of employees, but you might ask the employee a question that the manager knows the answer to, so the employee has embedded in it a pointer to the manager and is going to ask the manager the question. So that causes a cycle. Here's some code where we have, in particular, we have an employee that you can ask it, how many people work for your manager? And just the use case here is I have a user, and the user has a function called ask employee num staff, and it takes an employee, and we call employee on and it says num staff, so you're passing it in by const reference. And what the employee does is in its implementation, it goes and asks the manager, goes and finds out from the manager what it's the number of people working for the manager. And of course, this causes an upward dependency, which we don't want. So we want to fix that. And the way we're going to fix that is we're going to use an opaque pointer, which is uses in name only. So the employee is going to use manager in name only. And the way we're going to do that is we're going to take away the pound include from the employee. Here we have the employee is pound including manager.h, and we're going to turn that into class manager. And then we're going to change the int num staff const method on the employee to just give me that pointer, please. Tell me who your manager is. And then we're going to go over to the manager and we're going to put a public method on manager that says how many people work for you. And once we do that, we have this diagram again. Now it looks like this, where we have a client that knows about the manager, knows about the employee physically, but the method, this method still takes just an employee, even though it knows about both, takes the employee, and now the way it gets it, it says, employee, please tell me your manager. Okay, I have that manager. How many people do you have? So the idea here is the higher level user knows about the manager type, but doesn't know about the manager object until the higher level client says to the employee, who's your manager? But does know about the manager type, so this makes sense in the context of this higher level method. So I'm going to go back to this for one second more here. Hold on. This is what it looks like, and the client is at a higher level. So therefore, the client knows about the manager type, knows about the employee type. The employee does not know about the manager type, but the employee does hold an opaque pointer to the manager. Okay? So this works. You can do the same thing. The idea is within this ask employee function, yes, I know about these two things. I take the same argument, so nothing's changed. It's just the implementation of the function that I wrote at a higher level that's implemented differently. But I haven't changed the topology of my design, except for that. Yes?
This only, correct me if I'm wrong, this only holds true if the employee in the CPP file is not using any member function of the boss.
Okay, so what was said is this holds true only if the employee isn't calling any member functions of the manager. That is required, yes. Absolutely. And what we did was, before it was, and now it's not. Because the one case where it was, we changed it and said, no, you have to do this in 2 steps. You can ask the employee who your manager is, but you can't know the manager's business. And that works. This is opaque pointers. How do I deal with the manager is also employee? I changed the names in the example so that it fits my solution. Excellent. All right. I need a drink. All right. So one thing I would say is, you have the pattern, and what is it called? The composite pattern. And that is how I would actually probably deal with what you just said. But this is not the time or the place. Fair enough. Okay, but it's a worthwhile point. All right, dumb data. Sometimes you want something that's even more opaque than an opaque pointer. So this is this technique, using data that indicates a dependency on a peer object, but only in the context of a separate higher level object. So this is painful. This is, when you're doing this, you really mean business. You really want to do something special. So here we have a graph, and the node and the edge know about each other, and that's a problem. And the node and the graph both know about vector because the node has a vector of edges, the edge has a node as head and tail, and the graph knows about all these things because the graph is your wrapper object. And we don't want this. And I use graph because it just seems to be an intuitive thing for everybody because we know what's going on. And so we'll see this come up over and over as we go through the different techniques. So this is the opaque pointer solution to the graph, where we have the graph and the node knows about the edge in name only, and the edge knows about the node in name only, and the graph knows about everything, and you can ask all your questions of the graph and it'll just work. Okay. So here's an example of that, and you'll notice that we're including node.h and edge.h. They're both including the other guy. And now we're going to convert it so that now they're using them in name only, which means we get this picture. And that means we have to re-implement graph and change its interface so that all the questions are asked of the graph rather than the node and the edge. There are some other issues with this, by the way, that we'll address slightly later, but this gives you the idea. But suppose you don't even want that. Suppose you really want this, where the node doesn't know about the edge at all, and the edge doesn't know about the node at all. Well, that's interesting. How do you do that? So the way you do it is kind of Java-like in a sense, because what you do is you replace all the pointers with indices, and that's what we're going to do here. We're going to get rid of those class declarations entirely, and now everything is just going to be an ID. It's just going to be an indexed into a higher level array. And when we do that, we get this lovely thing, this graph .h, and we have node.h and edge.h and vector, and that's all included in graph, and they have vectors of nodes and vectors of edges, but the nodes store IDs, and the way we're going to have to deal with this is we're going to change all of those things to IDs. And now when you ask a question, you're going to have to do some interpolation. This is the opaque pointer version, and we're going to change that to this. The dumbdata version requires you to go through a translation in the graph. And the code is absolutely ugly, but it has this nice property. It turns something that is not externalizable into something that is externalizable. Like you can externalize a graph, but you can't externalize a node or an edge. But now you can, because there are no pointers, there are no process-dependent things. These are all fundamental types that are, we would call full-blown value types. So this is an interesting thing. This is the way we would write these kinds of functions now without the node or the edge knowing about the other type, not even in name only. So it's just a logical extension of an opaque pointer, Java style. Yes? Okay, so the question was, create an abstract type would increase type safety. Okay, so if you're doing this, you're already desperately low level. Might as well be writing in C. So I understand what you're saying. And yes, we could probably do some things to improve it, but in its purest form, what we've done is we're turning an ID and returning a pointer, which is a bunch of hex digits, into a number. And yes, of course, an edge pointer and a node pointer won't be confused, right? You won't confuse the two because they're going to be independent types. Whereas an integer, you could get them confused and call edge when you mean node and so on. So yes, you could create typed versions of that, but I didn't. But you could. I'm not saying you shouldn't, but you get the idea. Any more thoughts? The question is, can we use template parameters to do something with creating separate types? I think just creating an edge integer and a node integer index somehow where the types are distinct, would add some level of type safety perhaps. As a rule, just historically, I haven't been very big on turning integers into typed integers, just in general. And the reason for this is, and this might be a good place to do it, but for example, if I had something like, I don't know, age and shoe size, to me they're both integers, if that's what makes sense. And creating a separate type for each integer is more than overkill. It actually causes a loss in interoperability. Whereas having a date type compared to an integer is a very good thing, because the algebra of date and integer are dramatically different, whereas the algebra of the integer that's returned when you ask for somebody's age or you ask for their whatever social security number, those are integers as far as I'm concerned. So, but that's another topic. Anyway, yes, there are ways to make it safer. And in fact, that it's so unsafe is probably indicative of why it's so low level and ugly that we probably wouldn't do it unless we really were on a mission. And this would be done only at a very low level. It would not be an interface level. But I wanted to show it anyway. Yes?
The way I understood that question was, can we resolve a circular dependency by playing template tricks, like making it a node of T where T happens to be?
Okay, you're ahead of me. That is part 5 of the callback section. That's at least 20 minutes away. All right. Redundancy. When I first went to Bloomberg, I really got my butt handed to me because I had a tiny little bit of redundant code in a bootstrapping at the very lowest level of the system. This was 14 years ago. It was like heresy that I would ever think to have any redundant code at all in the entire system. Now, if you only knew how much redundant code there is, it's unbelievable that I was so chastised. But anyway, okay, deliberately avoiding reuse by repeating a small amount of code or data to avoid coupling. This is not as bad as it sounds. I'm talking about a tiny amount. I'm not talking about cutting, pasting, wild amounts of code. I'm talking about very surgical thing. But let's take a look at this. Suppose I have a large system and a small system, and I have some clients of the large system, and I have a lot of clients of the small system, okay? Now, everything is going along just fine, and I realize, oh, there's some redundancy. Oh my goodness, what am I going to do? So I say, oh, well, I'm going to get rid of that redundant code, and I'm going to depend on something else. So let's say that code is leap year. So that's not a lot of code, but maybe I don't want to have it in 2 places because I could get it wrong. Now, it turns out that somebody decided to have this redundant code, and unfortunately, it got it backwards. So it was about 1 February 29th ago when it was whether you could trade on the day or whether it was a trading day or not, and they just got it backwards. And so it worked up until that year, and then it stopped. So you really don't want to write complex code in a lot of places unless you're going to test it. If you are going to test it, then it's not as bad, but not everybody tests their code. So anyway, things change now. It turns out this is an proleptic Gregorian leap year, and oh well, it's too complicated. Let's make it really simple. Let's just have min for ints only, so there won't be any contention. Now, is it okay to repeat this code, or do I absolutely have to reuse this? And I'm going to argue it's okay not to reuse this if it's going to cause a problem. What problem could it cause? Well, let's say I take it out and I call this other thing. Now, that's not so bad because it's over here in this tiny little thing, and these clients are slightly unhappy because now I have pulled in a dependency on something for nothing, absolutely nothing, but all right, I did it. They're a little unhappy, but they just changed their link line and it's fine. Now imagine I go the other way and I say, well, I'm going to have this tiny little thing depend on this huge thing, and all of these people will come running to me and screaming and say, what are you doing? So that was a bad idea. Obviously, the right thing to do is to demote it to the right place in the physical hierarchy so that both of them can depend on it, and no one's going to complain because that's going to be in some central place, hopefully where they already depended anyway. Make sense? So that's the goal. Now, suppose you have a situation like this. Now, you can't win because if you do that, these people are going to complain, and if you do this, these people are going to complain. So you really can't do either. So that's not acceptable. You just can't do that. So unless there's a place to demote it, then don't do it. Bottom line is it's not worth it for that tiny little speck of code. So turns out for vocabulary types that are used widely throughout the interfaces of functions, you have to demote it. You can't have it in 2 separate places. So you have to think about these vocabulary types. And by vocabulary types, you think of something like a date, or you think of something like an allocator protocol, or something like that, where if you have 2 different ones, nothing works. So anyway. So here's another example. Suppose I have something at the bottom of the system, and I have this very it's very heavily used by this other higher level thing, and maybe this higher level thing has a really cool component at the top that does a great job. Maybe this is a wonderful threading implementation or something. It's amazing, it does everything. So it's well packaged, it's generally useful, it's awesome. But it turns out at the bottom of this thing, I need the simplest little lock or the simplest little bit that comes from this thing. Now, some people would say, well, just use it, just go ahead and depend on this thing. And now you can imagine, my head explodes, right? Because this is crazy talk. Now, you could also just say, well, it's not that much. Why don't I just move it down here? So I'm going to move a little bit down here, and it's not so bad. It's just a little bit. But it prevents this cycle, which is absolutely horrific. Now, this is the kind of thing I got screamed at for when I first joined. That was a long time ago. The culture has changed dramatically, and people don't really scream anymore. They just act, benignly. Okay. Anyway, over time, you can see that this thing could grow into something that's really awesome, and you say, you know what? That's not really that big a deal, is it? So I'm saying sometimes this is the right answer. I'm not saying cut and paste code. Please don't get me wrong. But sometimes you need to do a little bootstrapping, and it's okay, if that's the right answer. Okay, questions on that? Yes?
I think where this is really could be painful is header definitions. So if I have for example, an enum or a set of defines, I need to use two different components.
Okay, I heard header definitions and I heard enum or define. When I said vocabulary type, if there's something that needs to be shared, right, an enum would be considered a vocabulary type. So if there's something that needs to be shared, go across interface boundaries, that's one thing. Now remember also, if you can demote the thing to a lower level in the physical hierarchy, that's obviously preferable. Okay? Yes?
Why not always demote it? Like even a package group with a single package on a single component?
Okay, the question is, why don't you always demote it? What if we're really talking about int max, and you're going to actually create, package group, and then a package, and then a component, so, and you're going to have one little thing in there, and you don't expect that there'll ever be anything else. It's just not reasonable. That's why. Yes? You can be wrong, but guess what? Later you can demote it. And that, yes.
On the subject of demotion, not a C++ context, but if you haven't heard the story of leftpad.io.
I don't think I've heard the story. Maybe you'll tell me over a drink. All right. All right. Now, this was really the technique of last resort when I originally wrote the book in 1996. But it turns out that it has come into its own in the last 20 years. And so there are really 5 variations of this, even though they're really kind of all callbacks. So we have a client-supplied function or data that enables lower-level systems to perform specific tasks in a more global context. Now, originally the idea that I had was you have 2 things that are cyclically dependent, so you just have one install a callback in the other, and you kind of fake the idea that somehow they're levelized, but they're really not. This is just all syntax and it's all nonsense and stuff. So I really was very down on it in the original thing. I've changed my mind. It's still a callback, but you can do it in a much more respectful way these days. So there's several flavors of callbacks. So the first one being data, then function, functor, protocol, and concept. And that's what I said. We're going to get to the concept one, and that's some stuff. We'll get there. So the first one, we'll go back to the manager employee. And one way we can sort of do the same thing that we did before, but without making it, without doing a callback, function callback, is we can actually install in the employee a pointer to the member function or the data member of manager that is maintaining the count. So the idea is something like this. where we have class manager, and at construction, we install a pointer to the use count. Now that means we're returning the dereferenced pointer to some piece of the manager, and so we're going to create that separately because we don't have direct access into the vector. And then the idea is when we add an employee, we'll bump this count, and everybody who's an employee will pick up the thing we're talking about. Does that make sense? So it's just a kind of a cute thing. Now, it's effectively demotion. What it really is kind of like is this. We've pushed the int down lower in the physical hierarchy, but it's a fundamental type, so we really haven't done anything. We've just sort of a different incarnation of pointing back to some subpart of what we were talking about. Okay? So this is a variation in value. This is something that was pointed out by Tom Cargill. Inheritance is about variation in behavior, and data is about variation in value. And here we don't have a variation in behavior. We have a variation in value, and so we can just use a pointer back to the lower level data. All right. Next one is a callback function. And this happens often. You know, you'll have some application and it has some things that you want to install in a lower level library. But if we're not careful about things, maybe the lower level library winds up pointing to the or using the save and exit in main. Now, of course, this is ridiculous. No one would ever reasonably do this, hopefully. But anyway, stuff happens, so we don't want to do this. This is a cycle and a horrible one at that because it involves main. But with just a little bit of changing around, what we do is we make sure that there's a way to install a callback in the library. And that's a very typical thing to do. You install a callback, and in fact, the callback, now main has access to the callback, and it also has access to this specific module down in the library. And so the dependency is in this direction. So main installs the callback, and then the callback gets called by this lower level library when appropriate. And it turns out now that we have this save and add function that used to be external linkage, and now we can actually even make it static and local to main. We don't need to have it pollute everything else because even though it's static, you can still install it just like you could an external linkage function. So it's kind of cool. Something people do. All right. So here's another example. Let's see. Callbacks function. So back in the day when we had not wonderful things like functors, we would do things like installing a function along with its data, and it would look something like this. And there would be a cycle. And so it turned out we went to something that was a little better, where we had an event manager, and we would simply register an event and its data together, and then the function would have a void star, and it would point to the data, and the function would know to cast the data back, and life would be good. And life was good, and we could have the include in the any darn thing, or we could move it over to the implementation. It's all fine. And then one day we got functors, and then we said, you know, functors are better because they can wrap up the data with the in the function. So it's an invocable, and so we make a few changes and turn it into this, and change our scheduler event manager to look a little more like this, and then we change this schedule thing to look like maybe this, and if we waited till C++11, it might look like this, and life is good. So functors are better because they're more modular, and that's nice, but they're still callbacks, right? So not much magic here. So I'm going on to protocols or abstract interfaces. So I happen to like this game called Blackjack, and I've always actually started when I was 14. I was trying to figure out conditional probability. I spent the summer writing the entire tree for the game of Blackjack on a continuous piece of paper. It's a big tree. And I was using one of those microfine flare pens, and it took me many, many weeks to write this all down. But I did it. I don't know why. I was crazy. But I did. And I actually figured out what conditional probability was as a result. So that's a good thing. And I happened to go to MIT and learn blackjack well before the people who Kevin Spacey was talking about in the movie 21. I wasn't quite as successful as they were, though, because they really were out to make some money, and I was just having fun. Okay, well, that said, so here's my example. I've got the player knows about the game, and the game knows about the player, the game really being the table. And so there are things that you might break out. And this is all kind of just tongue-in-cheek, because if you think about it, what is a deck of cards? What does it really do? And some people, they think you have to have 52 card objects and all of that. Of course, that's all nonsense, but it still looks like a good slide. So I'm going to put it down here. And here, I have possibly the game of 21 and a player, and there's certain functions on the game of 21, and there's certain functions on the player, and they involve each other. And we need to do something about that. And a really good solution to this problem, and it is a problem because they know about each other in the interface, is to break the problem up into the abstract player that the game of 21 knows about, and the player, the abstract player, who has a notion of the game of 21 in the abstract pure virtual functions, but doesn't actually pound include the game of 21. And then the real player actually does pound include the game of 21. And here we have a levelized system, and it just works. That's it. It's that simple. It's kind of so simple, it's ill-making. And you could imagine that you could have every component in the world be an abstract interface, and every component in the world be the real version of that, and have every one of them depend on every other one like that. You really haven't done any good for yourself. But this is a technique of levelization in a pinch that you can use. But it does have a benefit. And the benefit is you can do more than one of these players. You can have, for example, a real player, a test player. So I can introduce a testing version of the player so I can, test the game of 21 separately before testing it with the real player. That's actually really important. And then I get really interested. Maybe I want to have a network player and start my own business. So this is getting cool. Now I can really do something fun and make some money. So this is a nice property of this technique that just happens to fall out. Okay, so the next thing I want to start trying to use things at a higher level through some sort of pointing back or whatever, but I know that's a bad idea. Let's say I do that. I create a backward dependency. Well, now these two components are cyclically dependent. Well, the other technique that I can do is I can create an abstract interface either in that component or below that component, where a higher level component now inserts the higher level component via the abstract interface into this component. And by doing that, I avoid the cycle. I do the same kind of thing of separating the dependency from the abstract interface. And I can do that there, but I can also do that on a larger scale. Suppose I want to depend on the thing at the top, which could happen, but it's no different. Now I've created this cycle across all these components. Well, that's not good, but I can do the same technique by saying the very high level component knows about the top of the pyramid, but it can insert the top of the pyramid into the protocol below this lowest level component upon which it depends, and I don't have a cycle again. So this is a very common technique when you have a bunch of stuff and you don't want to, you want to insert yourself in there, but you don't want to cause a cycle, so you create the lower level interface and the higher level actor, and then you can depend on it and it can depend back on the interface. So this is it's been used forever. It just works. There are many, many instances of this. Does this make sense? I'm just curious. A little bit? It does? Okay. Is anybody like wildly confused and said, what is that stuff he just did? No? Okay, good. Great. Maybe I won't sweat the book as much as I have been. All right. All right. So now we're going to talk about a callback as a concept, which is kind of a wild thing. I think it's wild. Someday we'll have concepts, and then we'll be able to do this. But even though we don't have concepts yet, it still works. So suppose I have, I want to be able to stream out the value of my value types. Date, time, account, all are value types. And I want to be able to stream them out in some sort of byte stream and then stream them back in later. So all of these things take a byte stream in the interface. And right now, this is what I've got. And they're all externalizable this way. And notice they're externalizable. They're flat now. They've been streamed out flat. And I just had to do this because I think it looks really good. Okay. So unfortunately, the byte stream needs a char buff to hold the bytes. But the char buff needs to be streamed out by the byte stream. What's up with that? So this is actually kind of the case where I got in trouble because I actually had a low-level string that didn't do much, and then I had a high-level string that did everything. And oh my goodness. But anyway, so I have the byte stream and the char buff, and they're, like this. They're including each other. It's very unfortunate. And that causes a cycle. And the cycle is not good. So what would you suggest I do? Having just seen what we did before, what would you suggest we do? Okay, so let's do that. Excellent. Let's do this. We could do this, right? In fact, we did do this. And then it looks like this. Can anybody see a problem with this? Okay, excellent. Now, I do want to point out that it is a myth, or if you saw the keynote, it is a frame that virtual functions are slower than, I want to say, inline functions. It can be true, but it's not always true. And in fact, if you have to say it, if you have an allocator that you've created on the program stack, the derived allocator, and you pass it in to a templated container, the client knows about the allocator's inline virtual function. Notice I said inline virtual function, and how it's used in the container. And if you happen to be working on GCC today, it's as if there were no virtual function at all, that it was just embedded in the type. We've already done that experiment. It's not so with Clang. So I'm encouraging the Clang ownership to start devirtualizing these kinds of functions where you have access to all the source and can do it the way GCC does. Okay? Challenge made. But it turns out there are cases where virtual functions really are too slow, and this is one of them. And so we're not going to do this. We're going to do something crazy. What we're going to do is we're going to define a stream concept. And the stream concept is whatever the interface to the stream utility, the stream object was. Whatever it was, that's our concept. And any type that has those methods and satisfies that contract is going to be fine. That's our concept. And then we're going to put the char buff lower because we can, because now the real byte stream depends on the char buff. And guess what? They're both going to mythically depend on this phantom concept that doesn't exist. And they're going to do, the char buff is going to do this, by the way, with the template method. What do you think of that? It's crazy talk. Okay, but it works. So now you have this char buff, and it's got this template method that takes a stream. You can pass in any stream you want. We're just going to pass in the stream we wanted in the first place. You could pass in a test stream, which could be used with extra sentinels to make sure that you really got it right, or the original production stream, or any darn stream you want to put in. So we got some more flexibility here, but we have absolutely no virtual functions. There is no overhead whatsoever. And now, notice again, this is a template function, templated on the stream concept. And now you just forget about the concept. It's just this. And it works. So this is crazy that you can externalize the char buff, and the char buff is used in the stream that externalizes it. It's all testable. So I think this is crazy. I think I love it. What do you think? Yes?
In this context, what do you mean by externalizable?
What I mean by externalizable is I have a byte stream, a concrete object that has put int 8, put int 16, put int 24, put int 32, put float 32, put float 64, put char, a char array, put, all of these fundamental types. And then I have the same get version of it that gets them out in a stream. And so when I say externalize it, I say, let me take all of your, whatever you want me to put in fundamental types, which it recursively could be nested or whatever into, whatever, and put them into a byte stream, save it out to whatever, send it over the wire, and read it back in again. That's what I mean by externalize. Send it out of process in a way where it can be recovered. And that's called streaming or externalization or whatever. Yes?
When would you use protocol over concept? Because if you have concept, you can implement some sort of concept that does the polymorphism.
The question is, when do you use a protocol and when do you use a concept? A concept is a tightly coupled situation and a protocol is a loosely coupled situation. So if you need high performance like you do in this case, clearly, you would use the concept approach, the template approach. If you need the decoupling, which we'll see much later in the next session, then you would use a protocol for sure. You can't scale compile time coupled things infinitely. It doesn't work.
Yeah, but my point is that you can make something that grabs the polymorphism and pass that into the concept, and then you can decouple inside that, actually.
So take the example, if you want a real example, take polymorphic allocators. That's like the example. We really do not want to have compile time, if enforced compile time coupling there, because we want it to be interchangeable. Okay? So, do we have any other thoughts on this? Okay. What is my stopping time now? 4:15. Okay. Ooh boy. Okay. So we have a manager class. Establishing a class that owns and coordinates lower level objects. So we have, for example, a list. Now, manager class really isn't a levelization technique, but it's an organizational technique, and it kind of fits in. We want to make sure we don't do silly things. We don't want to have a list that manages a list that manages a list that manages a list. It doesn't feel right. A list manages links. And we certainly don't want to have a link that manages links because that also doesn't feel right. Somehow, what we really want is some sort, we certainly don't want this crazy technique that was developed a long time ago that's designed to blow out the program stack, where you recursively delete the next link. We won't go there. So these are all ideas, but they're not necessarily good ideas. What we want is a list that manages a sequence of links, and the list is the manager class. And so we have something that looks like this, and it is a principle that we don't have types manage types. We have higher level types manage types, objects of that type. So we want a list of links. We don't want a list of lists, right? Now, obviously there are recursive situations where, who knows? But ideally, when we're building plain old straight normal things, this is a design principle. And of course, we would do it this way. So that's a list. Now let's go to, say, a graph. A graph is something where if you don't have a wrapper, it's really hard to make work. If you try to do this node edge thing, where you're holding onto the graph by a node, and the node is superior to the edge knows about the node in name only. This is a bear. Just try to do it. It just doesn't work. And the equivalent, the edge being superior and trying to manage the node in itself doesn't work. So what we really want to have is something like this situation where there's a graph, and the graph knows about the node and knows about the edge, and this, by the way, the graph is externalizable even though the node and the edge aren't. So that's what a manager class is supposed to do. And again, it's a strategy for dealing with ownership. It's not really a levelization technique, but I threw it in there anyway because I think important. All right, next, factoring. Moving independently testable sub-behavior out of the implementation of a complex component involved in excessive physical coupling. That's a mouthful. Okay, suppose I have a widget, and my widget, not a lot of accessors, it's just a lot of functionality that's thrown in there, and it's really big and it's really hard to test. What could I possibly do? Well, one thing I could do is I could pull, for example, a widget imp out of it, and maybe there are a lot of private methods, but in the widget imp, all the private methods are public. The widget imp is there for testing purposes. So I can test the widget imp at a lower level, but it turns out the widget imp has all these static methods in the implementation, right? So I can't test those, they're hidden in the implementation. So I could possibly break them out into an implementation util, bunch of static methods of a struct, and all those static methods are independently testable. So I start at the bottom, I test those, then I test the widget imp in terms of the tested functionality in the util, and then of course finally I test the widget knowing that most of the functionality is already working perfectly and I'm just wiring it up. Just like you take the chassis, the TV case off the chassis, work on the TV, put the case back on, attach the knobs, and it's all good. Okay? So that's the idea there. This is the architecturally significant client-facing interface. These are the private methods. They become public, and file scope static methods in the CPP file are made public in separate utility struct. Okay? Just a general telescoping when something gets too complex. Another example is you might have a date class, and the date class has a lot of complex functionality like a large cache for relevant dates to go from year, month, day to serial date. So that's another thing you might do, and here's your date interface, and here's your date imp util. And the date imp util takes most of the functionality away and puts it somewhere else, and you can test that, and then your date class is just your vocabulary type and value semantic type rolled into one, whereas the util is just a bunch of functionality that you can test directly. If you happen to re-implement the date class with another util, no problem. That one is still valid and can be used by somebody else, which is why we don't want to hide it. Okay, so now suppose we have this situation where we have a network, machine, and a cable, and it turns out that they all seem to depend on each other. And it was supplied that way by our, let's say our client. Our client said, I need this, exactly this, you have to implement it. And what can you do? Because it's a big cycle and it's a bad idea, but you don't have a choice. If you had a choice, you would not do this. You would do something else. And there are many things you can do if you have flexibility over the interface. But what if you don't? So what you can do is you can treat this as one component. And then you can factor out the independently implementable subfunctionality into 3 separate components. And this is often possible if you work hard enough. And you can test those things independently. Of course, this goes to level 2 now. But then, once you've done that, what happens to the higher level component? It becomes smaller. Fits inside its complexity bounds, because now all you're doing is providing the wrapper that refers to the implementations, the separate implementations. And this is basically what there is to factoring. There's probably many more ways to factor something, but this is basically the idea. Okay, questions? Okay, the question was why did the static members in the CPP file go to a utility class with static methods? And the answer to that is we don't think that free functions are big enough to merit having their own entity. We want to have a thing that is approximately the size of a class that groups the functionality into something that we can treat as a unit. So it's kind of like you have to go pick up all your marbles and put them in the bucket we'll deal with the bucket, but we don't want to deal with each individual marble as if it's comparable to something the size of a class. That's really the reason. It's also a pattern that we're very used to. When you see static foo-util and a bunch of, class struct foo-util and a bunch of static methods, you know what it is. It's just a very familiar idiom. And we don't want to go, there are tons of reasons why, having to do with not getting accidental overloads when you misspell the implementation in the CPP file in the namespace. And we don't want to deal with argument-dependent lookup because we're not interested in that. We want to call the function. We don't need an overload set. We don't need any of that. So there are a bunch of reasons. And part of it is habit. But it's fine. It works. Gets the job done. We love it. Another reason is you can't use using. We don't want you to use using. So just short. Okay. That's really the reason. There are a lot of reasons. There are like 7 reasons. I could mail you the reasons. I don't know if you'd like it, but okay. All right. So the last one is escalating encapsulation, and I hope I get through this one. If I go over by a couple of minutes, forgive me, but I really think this would be a good place to break. I'll try to do it as quick as I can. Moving the point at which implementation details are hidden from clients to a higher level in the physical hierarchy. So imagine you have car, engine, and spark plug. All right. They each have their own sphere of encapsulation. Each one of them is accessible by clients. What I mean by that is you can see that the car uses an engine. You can see that the engine uses a spark plug because it's used in the interface. Okay. 3 different spheres of encapsulation. Now imagine I change the car to use the engine in the implementation. All of a sudden, the engine is not in the interface of the client-facing pieces, which are car and spark plug. Okay? So when that happens, I just have a car. Because, yeah, the engine is using a spark plug in the interface, but I didn't know I was using an engine, so it doesn't matter. So effectively, when I say car uses engine in the implementation, the only thing I have is a car. Yes, I could go use an engine in another car, but this car doesn't have a way to know that I'm using an engine programmatically. So this is important. That means that what's going on between the engine and the spark plug, who cares, right? With respect to clients of car. Now, this is a kind of a interesting thing. What if I change the engine to fuel, the engine from spark plug to fuel, and you put a uses in the interface dependency from car to fuel? Well then, the car uses fuel. Who knows about the engine? It looks like this. Those are the new spheres of encapsulation for this system. Does that make sense in some very abstract way? The cool thing about this, we'll see, is that when something is not when it's not visible in the touch points that you're trying to present, it can change and your client does not need to rework their code. That's the key point of this. So, for example, let's look at our graph again. Now, right now we're going to add node data and edge data to sort of round this out. And here I have 3 levels. I have vector, by the way, is at 0. When I have something at level 0, it means it's external to this local subsystem. So now what are my spheres of encapsulation here? I have graph using node and edge, and I have node using node data, and everything is used in the interface. So basically, they're all their own deal, right? That's the way it is right now. The only thing that isn't, both graph and node, if you look, don't expose vector in their interface. So these are the 2 spheres of encapsulation right now, or the two joint spheres of encapsulation. Okay? Then suppose I say that I'm going to expose node data and edge data only out of graph, but I'm not going to expose node or edge. Now all of a sudden we get something that looks like this, where the only pieces of this system you know are graph, node data, and edge data, and whatever goes on inside underneath graph is whatever I want it to be. And you don't care because you don't know that I'm even using node, edge, or vector, if that makes sense. So this is another technique And this technique happens to be extraordinarily general. So it's important. Suppose we have, let's say this, and we want to put a single component wrapper on top of it. So I've got this nice wrapper. I can do this because it's all in the same component and it's all my business, and that's fine. I could do that if I wanted to. And they could then refer to this lower level, and my sphere of encapsulation is this, right? I don't expose any of that stuff. What I do is I have my own proxies, and I can reach inside the other one. My node can reach inside my edge and pull out edge because it's all in the same component, and I can have friendship going any which way I want to. So that's fine. But it doesn't work in general. So I'm going to show you for a multi-component wrapper. Suppose I have a date and I have a date set and I have this dependency. A date set uses date in the interface. And of course I can put date in the date set. Then I have my date. My date uses date in its implementation. It's a proxy for date. And my date set uses date set in its implementation. It's a proxy for date set. And my date set uses my date in the interface. All right, so I want to put my date into my date set, and you notice that I have these two spheres of encapsulation, but how does my date set reach into my date and grab date and put it into date set? And the answer is it can't, because it doesn't have access to the date through the my date interface, because it doesn't know. It's just another client. It doesn't know. So this in general isn't theoretically possible, or at least it wasn't until recently, but then I discovered some magic. So that's what I'm going to present as the last part of this. And then what you can do is make it a single component wrapper, in which case this works just fine, right? Because if they're in the same component, you have friendship, and you just pull the thing in and it just works. Single component wrappers don't scale. You can't have arbitrarily large single component wrappers. Another thing people try to do is they try to somehow hide a header file, and in that way kind of try to create some communication. Hiding header files is bad. You know, having the cookie go away, we'll just hide the cookie and you'll have this thing that takes a cookie, but we don't have the cookie header file, so what are we going to do? So this is a bad idea for two reasons. It convolves architecture with deployment, and it inhibits side-by-side reuse of the hidden component. So this is a bad idea. So now we're going to see the magic. It's hideous, but it's the best we can do. Imagine I have a whole collection of components sitting down here, and they all do all these crazy things, and we don't want to burden our client with all the work that we're doing down here because it's under development. So what we're going to do is we're going to clone this system up. We're going to clone it up, and we're going to make a set of wrapper packages. Now, it looks like this, where every single corresponding component with the same name, but it's a different package, depends on the corresponding lower level component in its implementation. And all it is a single data member. And now we're going to look at things where we say, well, I don't really want to show that dependency, so we just take it away. And it turns out, well, as a result of that, some things fall down. And then we say, well, there's some inheritance relationships. I certainly am not going to expose those, so I get rid of those, and they go away. And then I say, well, I don't need that, I don't need that one, so I get rid of that, and it goes away. And now what I have, I say I really don't like that sagging arc. I'm going to make that go away. So now what we have a view on the original system. It can't do everything the original system could do, but it can still do some stuff, and it's whatever we want to expose. Whatever components, whatever subfunctionality we leave in is what our view of our system is. And that means we can have really ugly stuff that could let things get out of sync at the lower level. We simply don't expose that functionality at the higher level. But how on earth do you reach in from one thing, get it out, and put it in the other when they're in separate components? So this is the crazy stuff. Imagine I have this left thing and this right thing. And in the wrapper, I have this left thing and I have this right thing. And the idea is the right uses the left in the wrapper, and the right uses the left in the system. And the right thing wants to grab the left thing's lower level piece and put it in the right thing. But it has to somehow get to it. So this magic that happens is every one of these holds simply the lower level as its only data member, and then we invoke something that's true in both C and C++ that people will not believe is legal C or C++, and that is we can actually know that the thing on the left, if it's there, it must have a corresponding lower level thing by the same name. It's required. That's what the rule of the package is. And so we can, believe it or not, we can depend effectively, the right can depend on the left by doing this ugly thing, which is a reinterpret cast. What I'm going to do is take the address of the guy on the left, I'm going to reinterpret it to be the thing it's supposed to be depending on, and then I'm going to get it back and I'm going to store it in this imp thing, this timp thing, and then I can just invoke it. And it's I know it's crazy, but you're actually allowed to do this kind of thing. So take a look at this. It's actually legal. It's guaranteed. I had Alistair Meredith look at it. And it's legal. So do you understand the concept? I have this thing. There's no interface to do it at all. But I know the dirty little secret of this package is everybody is shadowing something with the same name in the lower level package. Therefore, I can take its address, reinterpret cast it to the lower level thing, get back the reference effectively, and then use that in its place to put into my lower level thing. And it works. So you can tell me you hate this, and that's okay, but there's no other way to do it. And if we finally eventually had modules that had sort of package level friendship, it wouldn't be as good as this because that would expose everybody to everybody else's internals. And all this does is expose you to the public interface of the lower level thing, nothing more. So anyway, I'm going to stop there because I've gone over a little bit, but that was the last level piece of this. So we can take a break.